All right, let's dive in. Today, we are pulling back the curtain on something that runs our entire digital world, cryptography. It's this silent guardian that's protecting our information literally every single second of the day. So, how does it all work? Let's find out.
I mean, have you ever really stopped to think about it? You fire off a message, you log into your bank, you buy something online. All of that incredibly sensitive stuff is just flying through the internet. So what's stopping pretty much anyone from just snatching it out of the air? Well, there's a really clever science that's working for you right this second.
And this is it, cryptography. At its heart, it's really the art of writing and solving codes. It's the engine that powers all of our digital privacy, basically by taking our normal, readable info and turning it into a secret language that only the right person can understand.
So first things first, let's look at what this whole science is actually trying to accomplish, because it's about way more than just hiding things.
You're looking at what are basically the four pillars of digital trust. First up, confidentiality. That's the one we all think of, right? Keeping secrets secret. But just as important is integrity, making sure the message you get is the exact one that was sent, with nothing changed. Then you've got authentication, which is all about proving you are who you say you are. And finally, non-repudiation. That's a fancy way of saying you can't deny sending a message you actually sent. All four of these have to work together to create a truly secure space.
Okay, so how does cryptography actually pull off this little magic trick of turning our data into a secret code? Let's walk through the basic process.
It all starts with something called plain text. That's just a normal, readable message, like a WhatsApp you're about to send. That message gets fed into an algorithm. Think of that as a super complex recipe for scrambling stuff. But the recipe needs a secret ingredient, and that's the key. The key is like a secret password that tells the recipe how to scramble everything. And what comes out the other side? Ciphertext. Just a jumble of characters that looks like absolute nonsense to anyone who doesn't have that secret key.
And then, on the other end, the process just flips. Your friend's phone gets that jumbled up ciphertext. It uses the exact same algorithm, but now it uses the correct key to unlock or, decrypt the message, turning it right back into the original plain text. It's a pretty simple idea, but it's incredibly powerful.
Now, as you might guess, not all keys and locks are the same. The first major tool we're going to look at uses a single key for everything, kind of like a simple lockbox you might have at home. This is called symmetric cryptography, and the name gives it away. It's symmetrical. The key that locks the data is the exact same key that unlocks it, so the sender and the receiver have to share this one single secret key.
Now, the big plus here is speed. Symmetric methods are blazing fast, which is awesome for encrypting huge amounts of data. But it's got this classic chicken and egg problem. If you need a secure way to share the secret key, but you need the key to create the secure way, how do you even get started?
And that exact problem leads us to our next tool, which is, frankly, brilliant. This is the big idea that made secure communication over the wide open internet actually possible.
Meet asymmetric cryptography. Here's how it works. Everyone gets a pair of keys that are mathematically tied together. One is your public key. You can give this to anyone. You could shout it from the rooftops, post it on a billboard. It doesn't matter. This key can only lock data. The other key is your private key, and you guard this one with your life, because it's the only key in the universe that can unlock the data that was locked with your public key.
So understanding the trade-offs here is really the whole game. Let's just lay it out. Symmetric, it's the speed demon, uses one key, but sharing that key is a huge pain. Asymmetric, it totally solves the key sharing problem with its cool public/private pair, but it's much, much slower. It takes a lot more computer power. So as we're about to see, the really clever solution isn't to pick one or the other, it's to use them both together.
But hold on, cryptography isn't only about locking and unlocking things. There's a third major tool in the box that doesn't use keys at all. Its job is totally different. It's all about proving something is authentic. These are called hash functions. A hash function can take any piece of data, your password, a document, a whole movie, and it runs it through a special algorithm to spit out a unique, fixed-length string of characters. We call this a hash or a digest. And the absolute most important thing to know about it is that it's a one-way street. You can't ever turn that hash back into the original data. You can only use it to check if things match.
This is the perfect way to think about it. It's like a digital tamper-proof seal. If you change even one tiny little bit of data in the original file, the hash function will produce a completely different hash. So you don't need to see the secret stuff inside, you just check if the digital seal is still intact.
If it is, you know nothing's been touched. If it's not, you know the seal's been broken. Okay, so we've got our three main tools. We've got the one-key lockbox, the two-key system, and the digital fingerprint. So how do these things actually work together to protect you every single day?
This table is a fantastic summary. Symmetric is the workhorse, right? It's for encrypting the big stuff, fast. Asymmetric is like the diplomat. It's used to securely exchange those symmetric keys in the first place, and for things like digital signatures. And hash functions, they're the auditors, constantly checking for integrity and making sure our passwords are safe. So, for example, when your entire hard drive is encrypted, or when you use a VPN to secure all your internet traffic, yep, that's the speed and power of symmetric encryption just chugging away, protecting massive amounts of data in real time.
You know that little padlock icon and the S in HTTPS in your browser? Well, that's asymmetric cryptography kicking things off. Your browser uses the website's public key to start a secure conversation. But, and this is the genius part, it's too slow to encrypt your whole visit. So it does one very important job. It securely creates and hands over a temporary, super fast, symmetric key that will be used for the rest of the session. It's the perfect handshake, giving you the best of both worlds.
And how about your passwords? When you create an account, a good website doesn't store your actual password. No way. They store a hash of it. Then, when you log in, they just hash what you just typed and see if the hashes match. That way, even if they have a data breach, the hackers don't get your real password. It's also how you know that huge piece of software you just downloaded is the real deal and hasn't been messed with.
So you see, it's not really about one tool being better than the others. It's all about this really elegant combination, this dance between symmetric keys, asymmetric keys, and hash functions that creates all these layers of security that are protecting us constantly, usually in ways we don't even notice. But this field never, ever stands still. The very math that today's security is built on is being threatened by the rise of things like quantum computing. So the race is already on to invent the next generation of cryptographic tools. What will that look like? Well, that's the massive question that cryptographers are trying to answer right now to keep all of our digital secrets safe for tomorrow.